Yeah, hello to everybody, and thanks to the ECEEE for giving me the opportunity to present our recent report, How Energy Efficiency Cuts Cost for a 2-Degree Future, here in this policy seminar, and also thanks to Tyler for setting the perfect stage for presenting it by giving us the broad picture of the global developments and also the savings of energy efficiency that have been achieved in the past. Because I want to tackle the question of how much can we save by prioritizing energy efficiency in the national determined contributions for reaching the 2-degree target. Or you even see here that we are now a bit out of date with our title. It should be well below 2 degree or even 1.5 degree. I will shortly comment on that too, but in a way the question stays the same. Of course, as Tyler has told us, energy efficiency is very important for achieving the targets, but still there is some leeway between going for a pathway that has a lot of decarbonization options, so decarbonizing the supply of energy, or to more focus on reducing the demand to use energy more efficiently in the end-use sectors. So I will after a short introduction, I will tell you what we have done in this report and first show you the global results we found, but we have also focused on 6 focus regions. This is the US and the EU, China and India, Brazil and Mexico, and I will also at least comment on 3 of these regions, and we will, of course, later on hear a lot more about the EU, I guess. So the background, what was the main motivation for doing this study? So it was set up by ClimateWorks, and they asked the question, okay, everybody knows energy efficiency plays an important role in decarbonization, but what is actually the impact of a pathway that focuses more on energy efficiency compared to one that focuses on decarbonizing supply? And there's a lot of studies around on the savings that are delivered by energy efficiency in general, but here we really just compare, okay, we assume that we choose a scenario where we achieve the 2-degree scenario, but which pathway is the cheapest one? And okay, there has been some work in the global energy assessment, but I think this question wasn't answered before in this concise manner as we did it. And in particular, we also looked at the existing policies in the regions, as you will see, to compare which part of the potentials is actually addressed today. And you will see that there are also differences between the regions, and so this is not one answer for the whole world, but the answer differs depending on which country, which region you come from. So first, a short look at the history, but I think this has been mainly been said by Tyler already, that in the past, the biggest emitters have already achieved a significant reduction in energy intensity. I assume that you are familiar with reading this kind of diagrams, but let me shortly recall that this is, so the energy intensity is just the amount of energy spent per GDP, so it's the amount of energy used to produce 1 unit of GDP. And you see the development from the 1990s to the year 2013. And in the industry sector, so China started the worst, but they have also achieved the most significant savings, but still they have the highest energy intensities. So still they are not at the global average or even above the other high emitting countries. And a similar development can be seen for the transport sector for the US, who started out the worst, and with their CAFE standards, they have continuously been increasing energy efficiency, but still they are far from being as good as the other regions. And so you can already see here that for the other regions, it's even more difficult to reduce energy intensity to a significant amount, but there are, of course, a lot of potentials, and I will tell you more about this. So before going in the details of the methodology, let me give you a short glimpse on the overall results. So as I said before, we have compared 2 pathways, the energy efficient pathway, which of course, also has to include some renewables to achieve the 2-degree target, but to a much less extent than the energy-intensive pathway, which also makes use of nuclear power and CCS, depending on the region and in which amount. And what we find is that when we look at the cumulative savings from 2015 to 2030 of the energy-efficient pathways and this is net cost reduction, so we consider the investments, the operating costs and the fuel costs, and to a reference technology in a baseline scenario. And we find that the energy-efficient pathway saves $2.5 to $2.8 trillion when we accumulate the savings. And this uncertainty is related to the impact of rebound effects that you probably know better than me. Is quite there are quite some debates about the amount of rebounds we will see. And when we look at the annual savings only in the year 2030, then it's so the annual savings are continuously increasing, and they end up at $440 to $480 billion. And we also have looked at what have policies in 3 regions, China, the EU, and the United States, achieved in reducing the future costs to reach the 2-degree target. So because of the energy efficiency in the past, the increase of energy efficiency, we have to do less in the future, and this accumulates to $750 billion till 2030. Okay, now the whole story. So what we've done to assess our general goal to compare the costs of an energy efficient pathway and an energy intensive pathway, we have looked at the existing policies in the 6 focus regions and checked to which extent they already address the existing potentials. We have compiled a review of 2-degree scenarios and looked what is the amount of energy efficiency that is in these 2-degree scenarios. So there's a wide span. Some of them have a lot of energy efficiency in there, some of them have less, to get a reasonable region of energy intensities, a regional range of energy intensities that we consider then in our own projection of cost reductions based on energy efficiency policies and alternative decarbonization measures. And we did this based on an unpublished update of the well-known McKinsey marginal abatement cost curves. We looked at until 2030 for all 6 focus regions and had also some regional experts included to ground truth our results to the local policies. And so who was involved? It was, besides Fraunhofer EASY, we had the New Climate Institute and the Green Workers in the project team. And we also had a steering committee with well-known high-level stakeholders. Niels was there, but also Stephen Nadel from ACEEE and some other guys you may know or you may not. And we had the local experts. I don't want to go into the details here. It's just that to show you that we had regional experts from all of the 6 focus regions. And so now I come to the methodology and also to the results. So what you see here sketched is the typical marginal abatement cost curves where you see costs and benefits in the vertical axis. So the interventions shown here, they have positive costs, so they produce net additional costs compared to reference technologies, while those down here have produced, in a way, cost savings benefits compared to the reference technology. And on the x-axis, we just show the emission reduction. So this one would have a particularly large potential for emission reduction. And they are marked by color by the sector type they come from. So blue is generation, yellow is buildings and industry, and green is transport. And what you immediately see here is that, although this is just a sketch, the usual picture is that you find the end-use sectors more down here, while the generation technologies typically have, at least at the moment, positive net costs. So, of course, the costs from renewables are are reducing quite fast, but still they are more expensive than reference technologies. And then we chose the two pathways. So in the energy efficient pathway, we just included generation decarbonization options as much as needed to reach a 2-degree target, and we did this based on the 450 ppm scenario from the IEA that Tyler also showed to us. And then we chose a pathway where we focused on the decarbonization of the supply of energy and only included energy efficiency as much as needed. And so the first qualitative findings that you see here is that in the energy efficient pathway, we have the high efficiency in the end-use sector. It grants a significant flexibility in choosing how to decarbonize supply. Of course, here we chose the cheapest measures, or the ones with the least cost, but maybe for acceptance reasons or whatever, you could also just exchange those for one of the gray ones for a little higher cost, but you are flexible to choose. And a lot of this flexibility disappears when we look at the energy intensive pathway. And when we look here at the energy intensive pathway, we also see that we had to include, depending on the region, quite a number of energy efficiency measures to reach it, to achieve the emissions necessary for the 2-degree target. And so in total, we had to reduce the energy demand in the end-use sectors by 7% by 2030. And all in all, both pathways, they mitigate the same amount of emissions annually, maybe 5.4 gigatons. But as I said before, the annual costs of the energy efficiency pathway are $440 to $480 billion less globally. So let's take a closer look at the sectors. Here's a similar sketch where we have aggregated the results by sectors. And what you see here is that, so in the transport sector, we have the efficiency options like reducing fuel consumption of cars, or but also modal shifts in here. And on the other hand, we have this smaller bar here that represents biofuels and other options that are that are not related to efficiency. And you see that this one has much lower cost or much higher benefits and also a much larger potential. And for the industry sector, we see that the efficiency options, they are far more less cost intensive than the potentials when we look, for example, at CCS technologies or other process emission options to avoid emissions. In the building sector, so by buildings I mean both buildings and appliances, we see that the picture is more diverse. So there are options with very high benefits, but there are also options that are quite expensive, and therefore we just see here in the mean we just see a lower benefit than in the other sectors. But this just means that you have to look depending on the region. So how many buildings in our building stocks do I need to renovate, or to which degree, and so on. And finally, the abatement potentials of renewables and nuclear power, they are by far the largest. But if we want to fully exploit this, but you see that it has positive net costs, then it will be very expensive. This is what happens in the energy intensive pathway. And finally, the use of carbon capture and storage, both for power generation and industrial processes, can be avoided by at least until 2030 in this energy efficient pathway. We don't talk about thereafter because this will, it may be the case that we will need CCS there, depending on to whether we want to reach the 1.5 degree goal or the 2 degree goal. So now, coming from the general results to the more regional ones, here is an overview, and I will go into the details on the next slides, of the findings for the regions. So what you see here is the achieved emissions in purple that we took from the 450 ppm scenario from the World Energy Outlook, and the annual savings, and then the main potentials by sector, or the most important gaps that can be addressed by energy efficiency policies in the future. And so I immediately go to the regions. I will talk about China now, Brazil and the EU, but if you want me to, I can also comment on the other regions in the discussion. So for China, we find that actually already the intensive pathway requires a huge annual reduction of annual consumption. So by 14 exajoule in 2030, and compared to the current policy scenario of the IEA. And but still, the efficient pathway can achieve even higher savings. So depending on the rebound, 4.7 to 6 exajoule. And the realization of this additional savings will reduce net costs by quite a lot when we look on the total amount. But when we look at the savings per ton of CO2, it's 10 to 12 US dollar. That's not that much, but this is mainly reflects the fact that there are a lot of savings already in the intensive pathway. So now when we look at the historic and current policies, what we found is, as I showed you in the figure in the beginning, in particular in the industry sector, China has made a lot of progress with the top 1,000 and the top 10,000 program. And this has already decreased the future net costs by more than $50 billion per year. So this is really savings that are realized every year. And still there remain significant unaddressed potentials in the industry sector, in particular in the chemicals and the iron and steel sector, but also in petroleum processing and coking. And even more in other sectors like the transport sector, there are additional efforts required, like reducing fuel consumption by, for example, by installing very strong standards, or also by a modal shift in public and freight transport, where, of course, China is doing some making some progress on installing railways for long distances, but there's still a lot to do. So coming now to Brazil, here we find in total terms it's of course much lower savings, but the relation of the numbers is similar. That there are 50% higher savings in the energy efficient pathway, and the annual net cost reductions. Let me just say that here the savings per ton of CO2, they are much higher, and this is related to the fact that in the intensive pathway they don't need a lot of energy efficiency because they will mostly achieve their reductions by land use changes or avoiding deforestation, and therefore here we find much higher savings. And when we look at the current policies, so we didn't look at the historic savings here because there's very few data available on that, but also the impacts, as far as we could see, have been marginal when we can look at this global scale. And they have made some progress in the building sector with the Pro-Cell program, but also here there are significant potentials for retrofits of HVACs and air conditionings. And on the other hand, in the transport sector and the industry sector, they are really growing sectors in Brazil with strongly growing emissions, and there is a huge gap for introducing energy efficiency policies in Brazil. So coming now to the EU, though I have to say that probably most of you are much more have much more expertise for the EU than I do have, but let me anyway show our results for the EU to you. So here we find that the efficiency pathway, it can double the savings compared to the intensive pathway. And also this comes with very, very high additional savings when we calculate the savings per ton of CO2 emissions. So it's above $70. And so the reason here is that, on the one hand, that in the intensive pathways there is not too much energy efficiency needed, but also that the high cost economy that we have allows to achieve much higher cost reduction than, for example, in China. When we look at current policies, you see that historical policies have had a lower impact compared on the reduction of future costs. Again, this is related to the fact that in the EU we started at much lower levels of energy intensity and therefore couldn't go that much down as China and as the US, as I showed you on the historic slide in the beginning. But the EU is on a good track with the revision of the EED and a concrete energy efficiency target for 2030, though we will probably have some discussions about how ambitious the 2030 goal should be. The Eco Design Directive will, of course, also play an important role in the future. When we look at industry, the problem is that realizing energy efficiency will mainly depend on a reform of the EU emission trading scheme, which, as you know, has been dysfunctional more or less in the past in many ways. So here a reform is definitely needed from the point of the potentials that it can be realized, and also the only moderate fuel economy standards for LDVs and the lack of policies for HDVs, of strong policies for HDVs, pose additional potentials for improvements. Finally, also the retrofit of existing buildings is not, there's no standard for the whole EU. It differs by country, and there are a lot of potentials to realize here too. So to conclude, I just show you the results for all 6 regions in the overview, and let me just say that again we found here, as in many studies before, that when we look at just at the net costs of all these energy efficiency measures, they even produce benefits, and then you may pose the question, so why aren't they realized yet if the net costs are negative? And of course there are many non-financial barriers for energy efficiency measures, like the large amount of actors that is involved in realizing them, then the mismatch between the actors and the beneficiaries, and therefore it's really important to address these non-financial barriers, and this may produce some additional transaction costs, but the cost savings are that large that we can. It's not a problem to have to spend some money on transaction costs, I think. So yeah, that's all I wanted to say, and maybe I just point you to the fact that you can, of course, download the report. I'm sorry that I didn't provide the link here, but I also brought the 2-page summary. You can find it outside, and there you definitely find the link on where to download the study. Thanks.
Thank you very much. We also hear if there's any urgent questions for understanding here, we will take 1 or 2. We have 2 here first.
Thank you very much. Edwin Cornelis of Vito, Belgium. Thank you for your interesting presentation. My question concerns the basis of your research, the cost abatement curve of McKinsey, and actually I was wondering to what extent this cost curve has been validated.
Because ClimateWorks is also in cooperation with McKinsey, we were able to assess also the data that is not published by McKinsey, and there's even an update that has not been published but should be published soon of this, so there will be a version 3.0 of the McKinsey cost curves. And we could, by this we of course had some comparisons with other cost curves, and insights. By having insights in these data, we could verify that their assumptions are to a certain extent reasonable. But of course, as you know, there are a lot of debates about these curves, and so you should see this as a meta study of the McKinsey curves, and all the criticism that you can put to it, you can still be put to also this kind of analysis.
Please.
My name is Dirk van Orshoven. I'm an independent energy engineer here in Belgium. Basically, my question is the following. Are all energy efficiency measures included in this graph? Because I see on the left-hand side there are a lot of them which have a negative cost, which gain money. But if we take that triangle, and you could say approximately that's a linear curve, if we would have a curve going through it, if we would interpret that as a kind of law, how the energy efficiency versus cost measures are intrinsically available technologically and economically if fully developed, and we would extrapolate that beyond the 0 point, then there would be a much larger triangle with positive costs, so which would cost more than they bring benefit, but it would be much larger than the orange bars that you have here. So I always have had the feeling that in the study they primarily focused on those energy efficiency measures which pay for themselves, and the others are not fully taken into account, because generally you say we don't care about them. But if we compare them to the other options in generation, which have an extra cost, then there may be more energy efficiency measures that are still cheaper, but which are not included in the study and in the graph. Could you comment on that, or?
Yeah, so I think, so there are quite a lot here that have also costs in the order of the generation technologies, so these are included, but there are two kinds of cutoffs. So if the total potential of emission reductions is too small, then they were excluded, and of course there was some cutoff at a certain cost, though I have to say in the McKinsey data we got, there are some with even several hundreds of dollars per ton of CO2 emissions. We did an extra cut then here at $200. But yes, there are these kind of measures, but they are excluded for good reasons, I think.
But my question was mainly about those that are cheaper than what is shown on the graph, than the maximum on the graph. So the orange areas with a positive cost are very small areas compared to those with the negative cost. If we would extrapolate, well, I can difficultly explain what I mean, but if you would extrapolate that line with the negative cost, I would expect within the graph, within the range of the graph, much more energy efficiency measures still.
Yeah, okay, maybe this is really just a sketch. You shouldn't take it too seriously. It was meant to explain the methodology to you, but they may be broader than they are shown in the picture. If they had a significant potential and were below this cost level, then they were included.